I'm Cameron Davidson Pilon. Thanks for being here. I really appreciate it. Thanks for PyData for hosting this and inviting me. The title of this talk is Mistakes I've Made. So, I could ramble on a long time for how many mistakes I've made, but I've narrowed it down to like 5 or 6 sort of examples where I thought I was doing the right thing, something went wrong, and I'll explain what went wrong and how I fixed that, if I did fix it. So it'll be a very humbling talk. In retrospect, a lot of my mistakes are very embarrassing. You might catch on immediately as to like what the mistake is. If you do, awesome. Just don't shout it out. So there'll be lots of this on my face, like lots of like, oh, of course. Like, why didn't I do that earlier? So who am I? A little bit more about me. I'm the author of Bayesian Methods for Hackers. It's the online ebook to learn Bayesian methods with more like practical sense in mind. It's coming out in print soon in October. I'm the author of some open source libraries, including Lifelines and Lifetimes. And I'm a lead on the data team at Shopify. Shopify's headquarters are in Ottawa, Ontario, Canada. This is a map of Canada, unlabeled. I want you to think about where is Ottawa on this map of Canada. Just like make a mental guess. Everyone ready? Okay, that's Ottawa. Just kidding, that's not Ottawa, that's Ottawa, I think. So let's get into the first mistake I made. So this was a Kaggle competition. I did this in grad school with 2 of my close friends. We were just getting into Python at the time. Scikit-learn was just becoming like really awesome. So we jumped onto Python and Scikit-learn and started to attack this problem. The theme of the problem was we needed to predict the census mail return rate, and that's defined as the number of the number of census mailouts. That's the denominator. On top is the number of census sheets returned to the Census Bureau. So the data looked like this. It's at the block level. So think of block as like the most granular data when you deal with census data. Think of it as like a city block. So it's sort of aggregated at that level. The data looks like this. So there's the median income for that block, the margin of error for that median income, the fraction Hispanic, the margin of error for that fraction Hispanic, returned and sent. So this is what the raw data sort of look like. That's a very simplified form. So I'm predicting the return rate. So I just divide the times returned by the total, and I get this rate. Cool. That makes sense. I also don't need those margin of errors. Those don't really make sense. If my margin of error increases, why should my return rate increase? There's no immediate idea there, so I just nuke those. Then I do data science, so I just import scikit-learn and just use SVR, which was pretty good. Actually, this was a simplified version of what we did. We had access to, because we were in grad school, we had access to University of Waterloo's big, massive supercomputer, which was like awesome, 200 gigs and like 64 nodes. We were like giddy about this, so we were like SSHing in and running these massive like grid searches and ensemble methods. So this was like simplification, but we did some pretty crazy things. What was the outcome? That's a total failure. We came in like 41st place, and like we never really breached anything high. At the time, we had no idea what went wrong. Like we were so confident, 3 bright young gentlemen, and we just like threw up our hands. We had no idea what went wrong. It wasn't until months later. So I read this great paper called The Most Dangerous Equation. And if you get anything out of this talk, it's definitely check out this paper. It's such a good read. It's maybe 10 years old now, but it's just as relevant today as it was when it was written, and even like 50 years ago. So the author goes into discussion about what is the most dangerous equation. And you might think it's like Einstein's equations around like nuclear warheads or some sort of population growth model that might be dangerous. In fact, the author suggests that this is the most dangerous equation. And so in human readable words, it's the variance of the sample mean is equal to the variance of the population divided by square root n. Looks pretty innocent, but actually can get abused so easily. The paper has a great vignette about how it's misused. So there were some researchers doing some work in, you might have heard this story, but I'd like to repeat it. Researchers doing work in kidney cancer rates per county in the US. And the kidney cancer rates defined as the number of inhabitants, or the number of cases of kidney cancer divided by the number of people in that county. So they looked at, okay, which counties have the highest rate of incidence of kidney cancer, and they noticed there was mostly like all the counties in the Midwest. The researchers were like, yeah, that makes sense. I mean, lack of access to like good hospitals, high tobacco use, high alcohol use. So okay, that makes sense. And they also looked at the opposite. So which counties have the best rate or the lowest rate of kidney cancer? And they noticed that, oh yeah, it's in the Midwest. That makes sense. You know, access to clean water, fresh air, like hard work ethic. And so they came to opposite conclusions based on the same data. And the problem was they weren't considering the sample size of those counties. So the paper has this amazing picture, and if we were to plot on the y-axis the cancer incidence rate divided, or on the x-axis it's the population size of that county, we see this classic triangular distribution. And this is like a dagger in stats. Like if you see this, you have to be very, very careful. So what's happening is in these smaller counties, we have low populations, maybe like 100 people in this county. And if, say, 0 of them have cancer, then your rate is 0. If 50 of them have cancer, that's maybe a bad estimate, 10 of them have cancer, this kidney cancer, then your rate is 10%. So with these small data sets, or small counties, you have high variation in your estimate of the sample mean. And the sample mean in this case is the rate. So I saw this and I was so excited. I emailed my friend and I was like, I know why we messed up. And so I did the exact same thing for our data and to get the exact same shape. So some blocks have 2 or 3 people living on them. There was like a prison was one with like 1 inhabitant in that prison. So we see the classic distribution, and that was the problem with our data, and we didn't factor that in. We just, again, if I go back to what we did, our pre-processing, I had this data originally. I transformed it naively to this data, and I shouldn't have done that. If you look at the cent, it varies in its population size, and that's going to affect the margin of error in that rate. So that's where I messed up. So 538 yesterday actually they published an article about the best and worst board games, and the data looks like this. So again, classic distribution. So the y-axis is the average rating, the x-axis is the number of reviewers. So like that, this distribution, this triangle distribution, is classic in stats. Actually, it was funny when this was posted. A very predominant data scientist commented on it, and they actually fell for the exact same error that I fell for. They said, I'm very interested in these 2. And he circled the top 2 points. Now, if I go back here, like those top 2 points are probably not the best games. You know what I mean? Like those are, just by chance, they have some good ratings, but they're probably not the best games. So this individual fell for the exact same problem that I did. So what did I learn? I learned that sample sizes are so important when dealing with aggregate level data. We can't just discard them or ignore them. Interestingly, point 2 there suggests that if all the blocks have the exact same sample sizes, this wouldn't be an issue. The issue, if that was true, they would all have the exact same variance, and I could do whatever I want. But because there's different sample sizes per block, that became an issue. So what was needed to do was like a weighted linear regression or like a weighted something that takes into account the sample sizes. Using the margin of error, don't ignore it. I just discarded it, but the statisticians who gave me this data set, they put it there for a reason. I shouldn't just ignore it. That would have been very useful to have. I think that was the first thing I dropped, was the margin of error columns. Literally, it was just like, is MOE in column? If so, drop. It was that bad. And then number 4 there, I got burned so bad here. I like became a Bayesian because of it. It was so embarrassing. I was like, oh, and then when you think about from this problem from a Bayesian perspective, it's so obvious. It's like, oh yeah, you have to do that. You have to consider the sample size. And what I was doing is I was using like I assumed the rate was like a perfect estimate of that population, which was wrong. So case study number 2, I used to work in finance before I started at Shopify. And we used to do some trading, some day trading. So this graphic is intraday stocks for the S&P, the Dow, the NASDAQ, and the FTSE. The FTSE is like the UK index. That's the one in yellow. The markets open differently at different times. So suppose you are interested in doing some day trading. Your target is UK stocks, in particular the futures on the FTSE. So you go to Bloomberg or Yahoo Finance and you pull some data, and your data set might look like this. So you have time series. The FTSE, here I have the FTSE, the Dow Jones, and the VIX. The VIX is just like another stock. Your post-backtesting results look great, And backtesting is the financial version of cross-validation. How it works is you train on this portion of data, you predict on the next, and then you move ahead one. So you train on this portion of data, predict on the next, and keep doing that. It's like cross-validation, but sort of deterministic. So these look great. You're making money. Your P&L's through the roof. And then you push it to production and investing real money, and it sinks. Luckily, this didn't happen to me. It got caught. Like I noticed this mistake before it went to production, so I didn't actually lose any money. But it was an unobvious problem at the time. So what went wrong? Data leakage happened, and this is something I never really thought about before, except in like production data. So what is data leakage in this context? So if we go back to this graph, let's say I was predicting end of day prices for the FTSE, this yellow line, using end of day prices for the other three lines. Now the problem was the FTSE, or the other three lines, the red, blue, and orange, they contained information about the end of day price for the FTSE. So how does that work? So it was, if Y is the FTSE, that's the independent, or the target variable is Y, which is the FTSE. That was influencing X, these other three variables, which I was trying to use X to predict Y. So there was data leakage there. I wasn't really considering the FTSE's sort of like relationship to the other stocks. Does that make sense? Why that occurred? I'm seeing some heads, yeah? Okay, cool. So what did I learn? This was an important one. So your backtesting / cross-validation will always be equal to or overly optimistic, and you have to plan for that. You'll never get that 90% classification rate you do in your your cross-validation simulations. And number two is understand where your source data comes from. Understand it from like right from the beginning right to the end. So this was a case where I just naively used our data warehouse to pull end of day prices, ignoring sort of time zones and issues like that. But I should have looked at like, okay, where's this data coming from? What's that ETL process? Understand that part. The third mistake that I made was a testing mistake. So we saw two great talks yesterday about how to do testing by Trey and Chris. And this was a mistake that I made early on. So Lifelines is a survival analysis package that I work on. And one of the most important pieces in survival analysis is the log rank test. It's like the hypothesis test for survival analysis. I got an email one day from an individual using Lifelines, and he very sort of sheepishly, very like beat around the bush, the issue that, I compared this versus R, and I looked at your package, and I think there's an error. And I dug in a little bit deeper, and it was true. There was actually an error inside my implementation. There weren't like the p-values weren't far off, but they were off enough. So I had to fix the bug immediately, roll a new release, and release it. The problem was I didn't have enough tests for that implementation. So what I learned was when developing statistical software that already exists in the wild, it's best to test against that software. What I should have done is write my implementation, get a bunch of like input values, and then compare that output versus R's output, and actually hard code that R output into my test just to confirm and make sure I never do a regression. And secondly, just be responsible for software. I had to go onto like people's repos who were using Lifelines and like post a message saying, please upgrade to 0.7. Yeah, so that's the disvalue in open source software. There might be these bugs. The fourth mistake that I made was an A/B testing mistake. So this was right around the time I joined Shopify, and this was my first A/B test. I was super excited. I was like pro Bayesian. I was like, yeah, we'll do this Bayesian. It's all going to be good. So got the data, did the analysis. The Bayesian test told me that yes, these are significantly different. Control group had 4% conversion rate. Experiment group had 5%. I'm making these numbers up, but that's what it looked like. So upper management wanted to know, okay, what was the relative increase? What was like the lift on that experiment? So I just 5% minus 4% divided by 4%, 25% lift. So put that in Gmail, ship it, send it to the execs. I forgot sample size, and it's so important, that sample size number. So what happened? And you might have seen like headlines like this, and these always make me laugh. How a single A/B test increased conversion by 336%, or 211%, and below that it's like 140%. I saw one that was like 1,000%. increase, and the gentleman in the article called it a unicorn experiment, and that just made me laugh. So what's causing these like enormous lifts? Like what's going on here? Are these people just like getting the decimals wrong or something? So let's go back to that Bayesian A/B test. So if you're unfamiliar with Bayesian, I'll give you a quick like introduction what I'm displaying here. These are two posterior curves of the conversion rate for group A and group B. So this red curve, it's the distribution of what I think the conversion rate for group A might look like. So it's probably, the conversion rate's probably between like 0.3, can you see my, yeah, sweet. It's between like 0.3 and 0.5, probably around like 0.39, excuse me. That's the conversion rate for group A. For group B, it's probably between 0.4 and 0.6, so somewhere around there. So that's great, that makes sense, and my inference was correct, like these were distinct conversion rates, likely. So what I should have done next, and what I didn't do, what I should have done next is start sampling from these distributions. So I sample from the red distribution, I sample from the blue distribution, and I compute the relative increase. So sample from 1, I get P of A, sample from 2, I get P of B. So I have P of A minus P of B divided by P of B. That's like the lift. And I can do that thousands of times because it's cheap. And if I did that, what does the distribution of those relative increases look like? And it looks like this. So this is a very different distribution. It's very, notice how wide it is. It goes from like a bit below 0 to about, like up to 8 really. So this is the distribution of possible relative increases from my very simple experiment. So this is why you see these massive numbers like 300% and 1,000%. It's because there's so much variance in what that relative increase could be that, yeah, you might get 1,000%. Doesn't mean it is 1,000%, but it means just on that draw you got 1,000%. And this goes back to a problem I often talk about, and I like to talk about. It's the problem between, or the dilemma between the binary problem in A/B testing and the continuous problem in A/B testing. So the binary problem is which group is better. That's a binary problem. It's either group A or group B. It's yes or no, it's 0 or 1. The sample space is only like 0 or 1. So it's trivial to solve that problem. You just need to collect data and do the A/B test and you get the result. That's what the A/B tests or even like any hypothesis testing was designed for, the binary problem. The dilemma comes in when you try to solve the continuous problem. And the continuous problem is how much better? And that's a very, very different question. If you think about the range of values that problem could take on, or the solution could take on, it could be from negative infinity all the way to infinity. So really you need orders of magnitude more data in order to solve that continuous problem. But yet that's really what people want. People want to know how much more. They want to solve the continuous problem using the binary problem, or the binary problem solution. But the A/B test isn't designed for the continuous problem. So that's why you get these ridiculous numbers that look just crazy. Okay, so what do you do? You can't just like give your executive this distribution. That's very rude and they don't know what to do with it. So what you want to do is you want to pick a summary stat from this distribution. So I've labeled some points here. There's the mean is one of the most left. Yeah, left. My left. But that's the distribution is sort of skewed, so you don't really want to pick the mean because that skewedness is going to like push it too much to the right or left. Yeah, whatever. You guys know what I'm talking about. Or you can pick a better option is the 50th percentile of that distribution. That's pretty robust. Like it's not going to be affected by that skewness. I tend to find that is still a little bit too overly optimistic. I like to pick the 30th percentile. There's many reasons for choosing that. One that I like is that it underestimates the true value, so I'm being very conservative in what I tell my boss. That means they don't get all like crazy with like huge numbers. They sort of like remain sort of calm about the number. It also, what's a nice property is that it's efficient in the sense that if I keep acquiring more data, eventually the mean, the median, and the 30th percentile will all converge to the same number. So like I'm not being incorrect. So I like to choose the 30th percentile for these numbers. So what did I learn? I learned don't naively compute stats on top of stats. That just compounds uncertainty, like in nonlinear ways. You can't really measure that very reliably. It's better to underestimate than overestimate. So that's using that 30% versus like 50% example. So better to be like better to err on the side of conservative. And this is just more generally. I think visualizing uncertainty is the role of the statistician. If you think of any stats problem, and this applies to data science as well, if you think of any stats problem, hypothesis testing, or like a linear regression or anything like that, what the statistician is doing is actually taking all the uncertainty that they have and putting it in certain spots. So they might like stick it in one particular area and make it like very tight in one sort of like point, or they might put it over here, make it very flat, or they might like make it bimodal. So the role of the statistician is to like take that uncertainty and put it somewhere. They can't just like sweep it under the rug and give you like a single value. They have to like put it somewhere, and it's always present. It might be very sharp at one point, but it's always present. And that's what I did in this exercise. I visualized the uncertainty, and I saw how wrong I could have been. And then I based on that, I derived better estimates of what to do from there. Excuse me a second. So I have two more examples. One second. I have two more examples. These are a bit more mathy, so maybe I'll go a little bit slower. The first one is sparsifying the solution naively. I should have changed the title, but whatever. So let's say I do a regression, a linear regression, and I get these beta values. So I have 10. These are the estimated coefficients. So I have 10, 10, and 0.1. Assume the data has been normalized as well, so there's no like, well, this is a different order. This variable is a different order of magnitude than this one. Assume it's all like 0, 1, or like it's mean 0, standard deviation is 1. So there's no issue there. Okay, so it might be a good idea to like drop that loss variable. If you go back to this, like it's not contributing a whole lot to that regression. If x3, the third variable, changes a lot, like it's not really going to affect the response variable very much. Also say that that feature is very hard to generate. It requires like new data pipelines and like it's computationally intense. So it might be if you drop that variable, then you don't have to like create those pipelines and do that feature engineering, which is good. That's good. So that might not be a bad idea. Everything's okay, maybe? Well, suppose this is the true model. So x1 is equal to like normal 0, 1. It's not noise, like normal 0, 1 is just generating fake data. It's not like, don't think of it as noise, it's just fake data. X2 is equal to this weird 0.001 normal 0, 1 minus x1, I'll get to that. X3 is again normal 0, 1, and then y is generated by 10 times x1 plus 10 times x2 plus 0.1 times x3. So we did get the right coefficients. If you go back to that linear regression output, we got the right coefficients, 10, 10, 0, 1, 0.1. So we got that right. But let's go a little bit deeper. Let's do some algebra. So if I had 10 times x1 plus 10 times x2, if you just do the algebra, what I get is 0.01 times some data, some normal data. So actually, together, x1 and x2 contribute very little to y. In fact, an order of magnitude less than what x3 contributes. If you recall, the coefficient on x3 is 0.1. And if I combine x2 and x1, I get 0.01. That's an order of magnitude less. So in fact, these together aren't contributing a whole lot to y. So if I were to drop that x3 variable, I've like lost most of my information about y. Does that make sense? It's, yeah. I should have like an IPython notebook that does that. But okay, so what's the solution here? What was better? What should I have done? Basically, any form of regularization will solve this. It'll correctly. The problem was that x1 and x2 were highly, highly correlated. If I go back to that definition, you can see like they're super correlated. And so linear regression is not like it's a dumb method. It's not going to pick up on that correlation. Any form of ridge regression or like L1, L2 regressions or penalization, that will solve this. So if I did that, I get this. If I did even the slightest bit of positive L2 regression, I get this. So it looks a lot better. You can see that it's shrunk basically the coefficients of x1 and x2 close to 0, and it's maintained like a decent positive value for x3. So it's maybe like a bad example because like whoever does straight linear regression anymore, but it's just like it's a machine learning counterexample. It's supposed to be esoteric and fun. So everything's good. And my last example is PCA before regression. And this is something that sounds reasonable, and you might see it in like texts and in tutorials online, and even in textbooks or what your professor might teach. So PCA is great at many things, but it can significantly hurt regression if it's used as a pre-processing step. How does that occur? So suppose we wish to regress y onto x and w. Suppose the true model of y is x minus w, but we don't know this. That's hidden from us. Nature created that. We want to infer that. Furthermore, suppose that there is a positive correlation between x and w, say 0.5. So I apply PCA to the matrix xw, and I get this new matrix. I'm not going to read it, but that's what I get. That's just like PCA. That's what it's going to do here. And I've repeated it on the next slide. So that's the new matrix on the top. So any textbook, textbook on machine learning, your professor might suggest this, or a friend might suggest this. Like, it's good to look at the explained variance ratios. So if I did that here, I would see that the first column has most of the explained variance, about 80% of the explained variance. The second column has very little. So the recommendation from a textbook or a professor will be just drop that second variable. There's no information in it. You don't really need it. Okay, so you do that. And now we are regressing y onto this new column vector, which is 1 over root 2x plus 1 over root 2w. So now I want to find values alpha beta such that y equals alpha plus beta x plus w is a good fit. But there are no good values for that. Recall that y is equal to x minus w, so you can't find a good alpha and beta that really solve that. So this is actually a pretty good example. So here I have just like an IPython notebook. So I have rho is equal to 0.5. That's my correlation coefficient. I generate 1,000 data points. So W is defined. This is like how you create correlated variables. And so y is equal to x minus w. Cool. And you can see that, yeah, it's about 0.5 correlation between x and y, or x and w. So I do this. I import PCA from scikit-learn. I have n components equals 1, which means that I only keep one vector, the first vector, with the one with the highest explained variance ratio. So I have to create this new matrix called x bar, which is just like a fit transform of the matrix xw, which is exactly what I had in my slides. I roll that, and then I import linear regression. Basically do the lr.fit x bar y stuff. And what do I get? So this last number is the r squared value. So it's a measly 0.006. Oh, of course. Yeah? Sweet. So that's pretty terrible. So what happened? If I actually went back and did the exact same thing but didn't do PCA beforehand, I get an r squared value of 1, which makes sense. And that's what I should get, because y is completely determined by x and w. Oh yeah, quick IPython demo. We did that. So what did I learn? Or the solution to this, just don't use naive PCA before regression. You're losing information. Better to use, there's something called supervised PCA, or just don't do PCA before regression. That's another good strategy. Those are my 6 mistakes that I made in my time as a statistician / data scientist. Thanks for listening. Any questions? Cool. Well, if you have questions, I'll be around. Yeah.
Is it available?
Sure. Yeah. I'll tweet the slides, and that's the best way to do it?
Thank you. Yeah.
Sure. Yeah.
Given these are so non-obvious, and before you figure it out, doesn't that sort of make you want to give up?
Do you want me out of the field? Is that what you're suggesting?
Kind of like my own insecurities.
Kind of, yeah. Well, not give up, but I think we should start to share these ideas and this is where I messed up and this was the solution. I guess in interviews, in programming interviews, they often ask what's the hardest problem you've debugged? Maybe an equivalent for stats and data science might be what's the hardest, or what's the most counterintuitive result you've seen? Something like that might be a good question. But no, not give up. Yeah.
To that end, is there a book or a series of information you might recommend reading that would help you not make those mistakes?
Not really. We haven't.
It's really information, right?
Yeah, it is. It's just it's small little stories and vignettes about
Well, I guess what I would say is there's actually mental models that help you avoid those mistakes. If you have those mental models, you avoid those mistakes. If you don't, you go into them pretty quickly.
Right.
So,
Yeah.
have you teaching that helps you not immediately reach for a PCA. For example, there's well-known in statistical signal processing you don't remove data because your estimate's going to get worse, right? So if you were to come across that and try to do remove data, you're immediately wait, this is unsettled here, like immediately, because of that kind of prior education.
Right.
A quick path to this, rather than sort of man into the dark, you're never going to figure this out. There's actually a lot of information that can help people if you, do you really have to have a PhD in statistics, or can you?
Ideally, no.
Right, can you guide, is there a way to kind of guide the education, the pedagogy, with maybe a book, or a couple of books, or a series of
I think like blog articles would be a good solution, but like these need to be uncovered, or like those electrical engineers that would not throw out data, if they saw the analogy in what machine learners were doing, or like at least like beginner machine learners were doing with like PCA before like linear regression, just sort of like stopping them, or even like putting a stop to tutorials that suggest that before, yeah. But I don't think there's any books like that. There's an amazing book, this is sort of where it came from, an amazing book called like Counterexamples and Probability Theory, or maybe it's like Counterexamples and Stats, and that's sort of where the idea for like counterexamples and machine learning came from. So something like that would be cool for like applied stats. I think that's like pretty theoretical, the book I was talking about.
Statistics done wrong is a good book too.
Oh yeah.
And Ben Hamner from Kaggle has a series of like gremlins in machine learning, like
Cool.
mistakes we've seen.
Yeah, that sounds really good.
Since I think in generally this is kind of a new field, like in terms of the technology finally being in a place where more people have access to it, do you think any of these mistakes were perhaps because sometimes we don't have sort of the senior oversight, like in a lot of ways we're kind of pushing into newer territory in our respective industries, and there's not that senior experience to look over our shoulder and tell us?
I would say yeah, for sure. A lot of like small companies haven't hired like a full-time like experienced fielded statistician or data scientist. So it's like that financial example. I was the only like statistician at work, and I was like new out of college or new at university. So that was a pretty easy mistake for me to make. But someone who had experience would be like, no, you can't do that. So yeah, I would, but I mean, the field is really young, and companies are young, and they don't want to hire like a full-time, experienced individual. Say again?
They want unicorns.
They want unicorns, yeah. So to answer your question, like yes, that would be a good idea. Yeah. Yeah.
Yeah, my experience is statistics is a really dangerous field. For one thing, the literature out there is not very well standardized in terms of vocabulary and concepts. And so it's very easy to misunderstand things. And then also, it's so prone to biases, subtle biases, that you can't find in the literature, you only get it from experience. And for me, the only workaround I found was to get really good at simulating data. We had a thing on that
Right.
earlier, where you know what the true answer are, and you throw all your counterfactuals at it, and then you get an intuitive sense of where it blows up.
Yeah, I've thought about the idea of everyone hates like the first year or second year like stats courses in university. Like those are pretty bad. It'd be great to like reverse those on their head and like let's do a course on simulation first, and then we can do the stats class afterwards. Once you're familiar with like distributions and how to like simulate these things. So that'd be like a nicer approach to stats, to start from the simulation and then go into inference. Yeah, in the back.
This is more just a comment, but a really good source for these little vignettes of what can go wrong is stats.stackexchange.com.
Basically stats debugging, yeah.
Just get in the habit of kind of reading the interesting questions. You get a lot of really experienced statisticians who are pointing out people like, no, here's the subtle mistake.
Right.
Build up a library. It's kind of fun to read, so it's not hard.
A few of these were from there, so like I post on there pretty often, and I posted a few of these problems, and if you know Woober on that website, he's amazing, yeah. I think he corrected me a few times.
Yeah, just going in his history of answers is like,
That's his blog platform, yeah. He's really good.
it's worth all the tuition.
Yeah. Yeah, but I had to go back and forth. I wear the different hats many times. Yeah, so he's suggesting the Janes. Is it theory of probability or? Right. Yeah. 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 Cool. Okay. Well, thank you very much. I hope you guys enjoyed PyCon with PyData.